Well, thank you. Thanks very much, the organizers, for organizing such a wonderful workshop and for the invitation. It's great workshop here, and I enjoyed a lot. Although I have visited Florence many times, but this is my first time in life I was able to speak here, so I really feel honored for the organizer providing the opportunity to speak here. All right, so what I'm going to do today is a joint work with Kai Berend and Matt Pitti on BV infinity quantization -1 shifted derived Poisson manifolds. Some comments about the terminology here, as most of you might have now, CPTVV, Damien pioneered all those work recently on derived Poisson geometry. Which motivated a lot of activities in this field. So what I'm going to talk about here, in some sense, fits into that framework, but may not be exactly. So what I'm going to talk about, first of all, it's a symphony context. And also, may not be exactly derived. When you talk about there are derived derived manifolds, one way to think of derived manifolds, symphony manifolds, is think of a DG manifold for those DG manifolds whose algebra functions are negative graded. And so there's one way of thinking symphony. In that sense, that fits into derived manifolds. But for us, it's much more general than derived manifold. In fact, it's Q manifold. That's another thing. So should be a correct name. Probably should be this one should be a homotopy. Like a homotopy of Poisson manifold. Or shifted. Maybe that should be more correct name. The reason we picked up this name is it's more fashionable, you know? I mean, it just 20 years ago, everybody was talking about Q manifolds. And now a few people are talking about Q manifolds. Well, Thomas is here, right? People start to talk about DG manifolds. DG manifold, it's the same thing. It's a DG manifold more fashionable when you talk about Q manifolds. And not only people also, you could get the suspicious, like FBI will look at you because all the Q means something really suspicious. So that's the same. Well, anyway, so I'm talking about it here. It's in fact, it's very in the not just not so new the concept. See, in the supergeometry context was first by, I have a problem pronounce. I just write down the name. Voronov. Yeah, I have a problem pronounce this name here. Around 2008, they introduced so-called homotopy, Poisson algebras, and also homotopy Scoton algebra. Since they're interested in supergeometry, there are only two types. Either even, which is a Poisson, or it's just a Scoton. And in the Z-grading context, async Park and O, and Catania-Faldo called P-infinity manifolds. And this is more or less the homotopy Poisson algebra. So what I'm going to do is shift my odd Poisson geometry. So let me start with the definition. Let me remind you what a Poisson manifold. When you define Poisson manifold, is first of all you define what a Poisson algebra is, and then you define Poisson manifold. So let me remind you what is the what is the plus one shifted homotopy Poisson algebra. As I say, this is just a new way of calling something, the new terminal of something which is already appeared here, which is called homotopy Scoton algebra. In the only difference is Z grading. While KV, they were just looking at the Z2 grading, Z2 grading, a super language. So a plus one shifted homotopy Poisson algebra is a Z-graded algebra, Z-graded commutative algebra A with degree 1 bracket, multi-bracket, such that A with all the lambda n, here lambda n are starting with n bigger than 1, so it's now curved. So it's infinity 1 algebra. And the Leibniz identity holds for each argument. It's derivation. So you have Leibniz rule. It's a graded derivation. So if you look at if lambda n is just lambda 2, this is just a usual Gerstenhaber algebra. This is a usual Gerstenhaber algebra. In particular, one can easily see is you take a cohomology of this lambda n 1n, and this is become just usual Scoton algebra. This is just usual, either you call Scoton algebra or you call Gerstenhaber algebra, it's the same thing. Scattering algebra, Gerson-Haber algebra, or you call shifted one Poisson algebra. -1 shifted Poisson. All the same thing. You're taking cohomology. So that's the algebraic context, which I'm interested in. So exactly the extension, usual shift or scattering algebra into the homotopy, that higher order there. Question? Sorry, I probably should be +1 because algebra is a +1. Yeah, yeah. The manifold is minus shift 1. Algebra is +1 because yeah. The bracket is a degree, should be degree -1. Yeah. For some reason, yeah, the degree is -1. Yeah. And now, so what is the minus shifted derived Poisson manifold? Is just a z-graded manifold. And such that since I'm looking at infinity, so I can talk about global function instead of a sheaf. I don't need to worry about the sheaf. So I can call this infinity function. Sheaf global sections is +1 shifted homotopy Poisson algebra. Just like a usual Poisson manifold. Well, also, if you remember usual Poisson geometry, another way of saying this is one definition, there's a lot of equivalent definition, right? So a smooth manifold whose algebra is Poisson algebra. And that's the first definition. Second definition is using bivector field, right? You have a bivector field, scattering bracket equals 0. So here there's it's equivalent. There's an equivalent definition. It's the same thing. So equivalent definition is using instead of algebra, you can using bivector field. Here, since I'm shifted instead of bivector field, you got symmetric tensor vector fields. So just a DG manifold with pi. Actually, this is equal to infinity, so let me just a little bit to be vague. Should be direct product. It can go higher. So in principle, each pi n is, since I'm shifted, so instead of bivector field, n vector field, you can symmetric tensor. Such that this Moyaka-Dan equation holds. So this is the equivalent definition, like a usual Poisson geometry equivalent definition. And now the only thing, what is the bracket? The bracket here, it stands for so bracket is the standard Poisson bracket. on the symplectic manifold. Everything is Z-graded, but its usual things on cotangent bundle. On the cotangent bundle of M, there's canonical symplectic manifold structure, and therefore you have a bracket there. And now this is just polynomial function. This guy is just the polynomial function on Tm with degree n polynomial function, right? So you do have a bracket over there. So symmetric tensor are just polynomial, degree n polynomials. So that's the bracket, so Moyar-Cartan equation over here. So this is the equivalent definition. Well, so let me give you a few examples. Well, one is if you look at cotangent bundle, and here I have two Lagrangian. One is zero section, the other is just graph. DF. So the intersection, so this is a derived critical locus. In fact, this is a both are Lagrangian. And then the ambient space, this Z-gradient manifold, this curly M, in this case would be Tm dual shifted by -1. So let me write down the notation here. This is M, Q, and pi. Sometimes you can put a Q, pi together because the Q is just vector field. Pi is starting pi 2, pi 3, pi 4. So all those are similar. So in fact, you can put it together. But sometimes you want separate this to emphasize that I have a homological vector field here. So the Q is just contraction dF. And here you have pi 2. So this is only have one term. Pi 2 is, so here the function just polyvector field. We shift this sign. And Q is just contraction, right? Contraction. And then because I reverse the degree, so this is a degree +1 operator. And the pi 2 is just standard Poisson bracket. So this is kind of a baby examples of derived critical derived intersections. And in fact, Barbara and Kai Barron, they extend, they have a derived, I think that's more than 10 years ago, they did like a derived intersection to Lagrangians, so which is in the holomorphic context, I guess. But in the smooth case, then you need like a patching. This is like the standard example, it's a locally model of that ones. And so this is one examples. And for those people who are familiar with the Lie algebra, If you're familiar with Lie algebra, you can extend this a little bit. Instead of a tangent bundle, you can choose any Lie algebra. So you choose A as a Lie algebra. Instead of a tangent bundle, you can take any Lie algebra. Instead of a tangent bundle, cotangent bundle, you take A to dual, and then instead of a DF, you choose a section which is a cocycle. The Lie algebra cocycle. One cocycle is Allen-Bishop differential equals 0. So this is a IDF. IS, and here you have also a standard bracket, which is a basic, it's the same thing, Scoton bracket, so which is giving this pi 2 here. And this is another examples. And this basically will be derived intersection. Now in this case, AV is a so-called Lie Poisson, right? This is a Lie Poisson structure. This is no longer symplectic. It's Poisson manifold. And now you have zero section. And now graph of S is coisotropy. So you have a intersection, this derived intersection of a coisotropy. So this is a coisotropy of intersection of those two. And this will describe this intersections.
Is there a shift to the -1 in the...
Oh, yeah. Sorry. Thank you. Yeah. Everything just needs shifted, otherwise the degree is wrong. So basically, -1 is just Scoton algebra. But you look at intersection Scoton algebra.
Then here in the previous example, the F should be a Casimir? Or?
Where? Here?
Yeah.
No, this is you mean this one? The manifold.
Because you want also compatibility between the F and the pi? Or?
F is a function. DF is just the Lagrangian. So DF is just cocycle. It's a derived cocycle. It's a coboundary, right? Because the cotangent boundary DF, the Lie algebra D will be derived differential, which is 0. So. But you can replace this by closed form, one form. Closed one form works, which is also Lagrangian. You know, closed one form is the Lagrangian. Another examples, which is no longer derived in the sense. Because as I mentioned, if those two examples are derived, really you look at derived intersections, basically, derived intersection of either isotropy or either Lagrangian or coisotropy. But the other one, in fact, it's not derived anymore. As I say, this is more general. It's just in the sense of a Q manifold, DG manifold, which in the other direction. And this is infinite algebraic. So third example is somehow coming from the infinite algebraic. So if this is a vector bundle, it's infinite algebraic, which I may not have time to explain what is infinite algebra. I don't know if Thomas will talk about it. So this is, in fact, more general than Thomas, the paper he wrote, Thomas. So with infinite algebra, you can think of usually algebra, but the bracket no longer Lie algebra, but infinite algebra. But I think they require M is usual manifold. Here, my M can be Z-graded. And because of this reason, ankle map. So Lie algebra, you have ankle, you also have bracket. Ankle in my case, you can have multiple anchors, not one, you can have multiple anchors. So that's different. So again, giving infinite algebraic, you can construct. So in fact, infinite algebraic is the same thing as it's shifted minus 1 is a linear minus 1 shifted derived Poisson. It's the same, like if you are familiar with Poisson geometry, it's the same thing. What is Lie algebra? Lie algebra, you can either use, what is Lie algebra? Usual axiom, Jacobi identity, or the CIJK, what is the structure constant. Or you can say, on the dual of the vector space, you have a Poisson structure, which is linear. It's the same thing here. So what is the, basically I'm saying nothing here. So what is that I mean by linear? Linear is just a vector bundle. So here's, you just need a linear respect to the weight. Let me just, so you can consider the actual definition of infinite algebraic, what I'm trying to say here. So here, the function, again, so if I look at this function, so function on this Z-gradient manifold smooth function, again, here I'm just looking at the global section, are just section of symmetric tensor take completions, right? So that's the functions. And so what do I mean? So now you have a bunch of those bracket. Lambda n, eating k, spit out. I think this is what it means linear, just putting the weight. So 1 minus n. And you can see if the usual n equals 2, that's exactly just means a linear section, bracketed with linear section, still get linear section. You look at n equals 2 case. So this is an extension of a linear structure. If this homotopy Poisson is linear in this sense, then this is infinite algebraic, and vice versa. So that's another way of thinking. And this is the one example which is not derived in the usual derived. The other thing.
Are you asking that M be
Z-graded.
only Z-graded?
Any Z-graded. So L. So in fact, yeah. So this. No. So L, sorry, just this is Z-graded vector bundle. This is Z-graded vector bundle. Then the conclusion is infinite algebraic is equivalent to this dual manifold. And then this definition here, by the end, where it encodes the anchor map. You look at some special case n equals 0. Maybe this I need n equals 0 or what. I know I forgot. And then you will automatically M has to be a DG manifold. You have a Q there. This will come from the axioms. Yeah. Sure. So let me move to the quantization part. And now, since I'm looking at all the z-graded, instead of density, you can talk about also density, half density, but they use Brazilian, right? So instead of what is really matters here, I think this is probably in Az's talk. He used densities also. So density, this is just a Brazilian half densities, which is a line bundle over M. And you can look at differential operator, acts on here. In the usual way, you can talk about the order of differential operator. This is just the differential operator acting on this, the line bundle, section of, or more precise, should be section of line bundle, right? Of order of most order of n. So, so the usual, everything is the usual, there's no difference, z-graded or usual manifold, it's the same thing. So you have a filtration, which satisfy the orders of very standard differential operator series, which adapt to z-graded, but there's no difference. You have the composition of order n is differential operator n plus m. The bracket right? So it's the same thing. And now you can take a GR, graded associative algebra, which is definition is just the differential operator degree n quotient by order of less than n. So one can easily prove this is isomorphic, symmetric, it's symbol, right? Everything correct. So all those are standard differential operator theory works for z-graded. Everything just standard. I mean, there's no difference. Since I'm looking at all the smooth category. So you can also define what is principal symbol map. And it goes to basic GRN, which is isomorphic to V. So giving any degree, order of undifferential operator, you have a principal symbol. That's the same thing. So this is what defined. And now, a definition which has been, I think, over 25 years or so by Olga Korchenko. I don't know if it, again, I apologize if I pronounce her name wrong. Introduced so-called BV infinity operator. In a proceeding of a Barnard Center publication, published in 98. So it's exactly 25 years ago. So the definition is you got an operator. I'm going to put in the H bar here. And now each operator is maximum order of n. And degree of each, now you have a degree, so because z graded, so the degree is 1. And the square is basically is 1/2 because the degree 1 is so bracket 1 is 0. So this is a BV operator, BV infinite operators. I don't think she used the half density. She used a function, but the principle is the same. The only thing, the difference here, I'm using half density is more intrinsic. So a proposition.
Is there n or n plus 1?
Here's order. So order is at most n. If n is n. So degrees are always 1.
Yeah.
So as degrees are always plus 1.
But in usual story, it's degree 2 as an operator, it's second order.
So it's a matter of convention here. I'm choosing, for instance, if the homology vector field, I'm putting the H here in front. And normally you don't. So yeah, it's just convention. Putting H here, yeah, it's just a convention here. So a proposition, which I think due to Olga Korchenko, I think she basically proved a BV operator, BV infinite operator generates to basic M is minus. I'm putting the the modern terminology is a -1 shifted derived Poisson. In fact, the proof is very simple. How to get those brackets is just derived bracket. There's the usual way of doing derived bracket. So the proof is what you do is what is the lambda n? Lambda n, you need n functions, right? And if you want each n function, and in fact, this is just you take the commutator from delta and f up to the, you take n times. S is just the symbols, the section of the density. And you can see because this operator delta delta n. So I should say delta n. So since delta n is a maximum order of n, you take a commutator n times, so then you get degree of the order 0, which is a function, right? So, and that's just, so this is basically, you can try to say this is, you can see this is infinity one algebra. So that's the idea. If you prefer tensor instead of bracket, and then instead of a bracket, this tensor, in fact, this guy will be just taking the principal symbol. So you take each of this, you take a principal symbol for each n and letting h equal to 1. And that would be, okay, because you're taking principal symbol, that's symmetric tensor, and that's just pi. So that's, in other words, how to, so this is again, those are the Poisson tensor. So elements here are Poisson tensor, or well, shift the Poisson tensor. Everything's shifted, right? So instead of multi-vector fields, it will be symmetric tensor. And you can have infinite many, so you got a completion here. Well, let me show you one example. If I have only one term, yeah, that's probably difference. Here, H2 instead of H1, just only one term, delta 2. And so in this case, again, this is degree plus 1. Order 2, maximum order 2, right? Operators on densities, half densities, right? So assume I have, which is just pick up a nowhere, because this is a line bound, always you can have a global section on 0. So let just pick up a row is I see. Just a section. Such that zero, you can have pick up a section. And then you can convert this operator into operator on functions. So instead of acts on the half density, you act on the functions. And now you can easily see this operator against square equals 0, and this is degree 1. And the bracket, which I just wrote down here, and now you just n equals 2. If you play around your formula, putting n equals 2, you write down what lambda 2 is. So lambda 2, which I call Fg, probably it's not Fg, so probably write in this way because otherwise people are always confused with Poisson. So this guy is just lambda 2 Fg. This is, if you write on the commutator, you can see this is just the Fg minus I think that's it. So you can see this is just classical BV operator. This has become usual classical. You see all the literatures. And so if, in other words, if you have one term, this will be, then this is just classical BV, classical BV operators. And so now you can trust me if you have a higher, and then you got the just homotopy BV, homotopy BV infinity. So just you have all, so more terms. All right, so what is a quantization problem? That's, I think I'm almost getting to my, is quantization problem is let be a shifted derived Poisson from a self-joint BV infinity operator such that the, it's derived bracket, it's giving one, so I'm using more h equal to 1 is equal to q plus pi. So this somewhere, yeah, this one called, yeah, this by definition, sigma h stands for, I'm taking each of n, taking its principal symbol bond, symbol map. So, and that's quantization problem. What the self-joint means. So self-joint, well, since I have half density here, so you can talk each operator, you can talk a dual operator. But then basically, then you need the h dual is defined to minus h. So h dual to be minus h, and then, so in other words, self-joint means if n is even, this operator has to be even, a self-joint. And r, if n is r, means this operator has to be anti-self-joint. So in other words, delta n dual equal to minus n delta n. This is a self-joint condition means. What? There's a natural pairing because I'm looking at operator on half density now. So half density. So otherwise you need, so that's why I, instead of the differential operator on function, I use differential operator on half density. So on half density, you have natural pairing. When you pair two half density become one density, you take the integral. So there's a natural pairing there. So you can talk about the intrinsic, what is, yeah, that, otherwise you need some work. So that's the advantage of talking self-joint. All right, so now, how many minutes? I was not quite sure. It's 1 hour or 50 minutes. I'm not 55. Okay, so 5 minutes I should be. All right. So then I just write down the theorem. So so first theorem is a quantizable. Is quantizable if second Poisson cohomology is 0. So this theorem, basically, it's analog of if you're familiar with deformation quantization. Initially, there is one Gerstenhaber developed deformation quantization. You do each term. One term, you go to the other term, you look at obstruction, and then this is H3 cohomology equals 0. So it's analog of that. So if the Poisson cohomology, you can define, because here I have a Poisson, using bracket Poisson cohomology. If this is equal to 0, and then this is quantizable. But in most of the cases, never 0. This is never zeros. This is never 0. So this, so to prove this, what we did is, in fact, this guy. So classically you derive minus one shift derived Poisson is a DGLA Moyaka-Dang equation I already explained to you, and then the quantization is another MC delta square equals 0. You can interpret another DGLA. So basically become a lifting of a Moyaka-Dang element to a Moyaka-Dang element of a DGLA, and then you kind of split it into different sequences, a lifting problem. So that's one question, which in general, this is not useful because, as I say, the most of you never 0. So second, we gave a positive. Nevertheless, if it's a linear, if it comes from an infinite algebroid, and then this is always quantizable, canonical quantization. So linear minus 1 shifted derived. Not only always we have a canonical, you can construct a canonical, admits a canonical. Quantization. Last one is for the derived intersection, which I gave you as examples. In fact, one can construct very canonical quantization. So for this one, this has a canonical quantizations. Which, if you, now let me just comment. So what is, you can write down explicitly what is our quantization is. Let me remind you what is a Brazilian, in this case, AV. And this, you can identify the section, pullback section of A top degree tensor top degree of Tm. I think this will be V. That's Brazilian half density. So you can write down canonically a quantization using, I don't have time, using so-called Lou Weinstein absolute one-sum module for the algebraic. And just one, let me just finish. Let me just give you one example in the case of special case. This instead of usually algebraic, it's just tangent bundle and just derived critical locus, and then this quantization, this operator is H. This is Q, and the second order is, in fact, this is just, you go back to, this quantization is going back to Kouzou. I think this is basically the Kouzou operators. So this is a, so phi is the isomorphism differential form. To top degree minus k. So you play around the isomorphism here, and then you take a drum differential here, you pull back using conjugation, you got an operator here, and that's BV operator. So this is really what I think 85. But the only thing is you need to add the first term. I think that's it. And then the algebra is a little bit extension of this. So I stop here. Thank you.
Just to clarify, to understand better something we made. So what is being before this quantization? That's the first part. Quantization is always kind of deformation.
No. In this case, I'm not. So it's not that. Well, depends on what you mean by definition. Here is a quantization is as a defined here is basically you want a BB infinite operator whose principal symbol is the derived back is a Q plus. Yeah.
If I think of like the more physical interpretation, would it be correct to say that this delta it has to be interpreted as a quantum DRST operator acting on some? Of course, this is differential operator, so it acts on functions. These are like wave functions, right? It smells like quantization of generic constraints.
Maybe I'm not quite sure. I'm not familiar with this. Maybe someone who knows physics knows better. Thomas maybe can help me answer that question. So I'm not quite sure.
Yeah, this I understand, but I think it is. Okay, maybe we can.
So these PV infinity algebras, are they also more or less the same morally as this loop homotopy algebra?
What algebra?
This loop homotopy algebras, which are marked
I'm not sure. I'm not familiar with that. Yeah.
ideal infinity algebra.
Involute. That I'm not sure. So yeah, I'm not. Yeah. Maybe Damien knows. No, you guys play around those too. So no, I'm not familiar with that. Yeah. Right.
So is there something like that in
I was expanding. I understand where you are from. So initially, it's true. If I have a delta 2, if n equals 2, and this operator is all Laplacian, yeah, that's what you call this. The BV operator is the same thing we'll call all Laplacian. Exactly like what Azza was talking about. Because integration is invariant under the like Lagrangian deformation, right? Integration. So I hope this is similar, but I'm not quite sure.